In this example, we're going to solve for a parallel pipe flow application. What we have is we have a pipe that is originally carrying 300 cubic meters per hour, which is equal to 0.083 cubic meters per second. And again, to get that, I just divided by 3,600. There's 60 minutes in an hour. Okay, in a minute you have 60 seconds, so you just divide by 3,600 and you get 0.083 cubic meters per second. So what we have is we have a flow in a pipe that's approaching this point where it splits off into two parallel pipes. Okay, pipe number one is 325 meters long, and it's a 150 millimeter diameter pipe, which is roughly, in English terms, that would be like a 3-inch pipe. Okay, pipe number two is a longer and larger pipe. It's 600 meters in length, and it has a diameter of about 250 millimeters, which would be like a 5-inch pipe. And so what we're trying to figure out is if we have 0.083 cubic meters per second that approaches this point here and it's going to split off between these two pipes, we'd like to know how much of that flow is going to go to pipe 2 and conversely how much of that flow would go to pipe 1. Okay. A key assumption in this problem is that we're going to assume that each pipe has the same friction factor. Okay. By doing so, basically we're saying, okay, each pipe is going to be the same type of material. So it's either cast iron or PVC plastic or whatever it might be. And we're going to assume that when you go through and you do the Reynolds number and you go through and do the relative roughness and get the friction factor, those friction factors are going to be about the same. Okay. Is it always the same? No, but friction factors tend to range in the 0.02 to 0.028 range. And it's likely that they would be close enough in this application. There is a problem that we're going to do later on in the course in which we don't make this assumption and we actually have to go through and step by step go through and redo the Moody diagram. So let's go ahead and get started. Now essentially we have two tools in our toolbox for solving this problem. The first thing we know is that if we have flow in a parallel pipeline, okay, that the flow is going to split as such that the head losses from friction in one pipe are going to equal the head losses in the other pipe. So I'm going to start with that. I'm going to start by saying, all right, the head loss in pipe 1 is going to be equal to the head loss in pipe 2. Okay. In this problem, we're not looking at minor losses, we're looking at just friction. So the friction in this problem, we're going to use the Darcy-Weisbach equation. We have F1 times L1 over D1, V1 squared over 2G, and then for pipe number 2, we have similar expression, just subscript 2. So we have L2 over D2, and then we have V2 squared over 2G. Okay, and again, assuming that we have the same friction factor, we can go ahead and cancel these terms, and I'm going to go ahead and just cancel out the 2G's as well. Okay, so now working at this equation here, the length of pipe 1 is 325 meters. Okay. The diameter of pipe 1, it's a 0.15 millimeter, which is equal to 0.15 meters. Okay. And then we would have V1 squared. Okay, for that term there. And then on the right-hand side, we have a 600 meter long pipe. The diameter is 0.25 meters. Again, I'm just making sure the units balance out. I want to make sure that if I have meters in the numerator, I have meters in the denominator. And then this would be the V2 squared. Okay. So when I plug this into my calculator, taking the square root, I get the V1 is equal to 1.05247 V2. I normally don't carry that many decimal places, but in this particular case, I'm doing it just because it's something that we're going to be carrying through several calculations. Okay, so there's my first equation. Now we have two unknowns. We don't know what velocity 1 is, and we don't know the velocity 2. So we're going to need two equations. So this was our first equation in our toolbox. The second one I have available to me is knowledge that the flow of 0.083 has to split up into two separate flows. They split up and then they join back, and when they join back at 0.083. So basically what we're saying is that the total flow, which is equal to 0.083, is equal to the flow in pipe 1 plus the flow in pipe 2. It's not going anywhere assuming we have no leaks or other losses in the system. Okay. From conservation of energy, we know that the flow is equal to velocity times the area. So this term here we can express as 0.083 is equal to, this would be V1 A1 plus V2 A2. Okay. What I'm going to do is I'm going to go ahead and substitute this expression I have for V1 in here. V1 is 1.05247 V2 times the area of my pipe. I've got pi over 4. It's a point, I'm sorry, this is V1, right? So we've got the 0.15 meters squared. We're going to go ahead and carry this on the second part here. Then we have V2 times that area of the pipe, which is pi over 4. And this one is 0.25 meters squared. Okay. And when I take all this and I solve for V2, I get that V2 is equal to 1.226 meters per second. Okay. Now the question is how much flow is going through the pipe. It's not a question of what the velocity is. But again, using this equation here, using the relationship conservation of mass, that the flow is equal to the velocity times the area, we can then solve for the flow going through that pipe by just taking the velocity that we just computed, multiplying it by the area of that pipe, okay, and we conclude that the flow going through that pipe is 0.06 cubic meters per second. Okay, so essentially what happens is if we have a flow of 0.083 at this point, 0.06 is going through this pipe, the remaining 0.023 would be going through this pipe. So roughly 2/3 of the flow is going through this pipe, 1/3 of the flow is going through that pipe. And that concludes this example of a parallel pipe flow.